better. Thanks. And also, to consider the last 3 days, we have done a lot about fatigue assessment, crack calculations, and the crack assessment, and also the critical cracks. And what I want to do today is like to close the circle, to have the sentence, and to get also the point on the variable loads and how we can go there and give there an idea how to define the collectives, and at the end go again into the fatigue design and recalculate the fatigue damage. So as I had yesterday some questions regarding some literature, I have here 2 books which I like to work with, just regarding, of course here the point is the welded joints, but also the topics around are actually good explained. And so this is a more, I would say, scientific orientated book. And this one is a book which is related to offshore structures, and therefore gives also some workaround, some examples on specific details, on some specific examples where they took out a part, did some analysis, and afterwards also give some good recommendations. So this is regarding to fatigue, regarding to fracture. There is, I know the picture is not really good, but it was actually the best one I got. Is called Fracture Mechanics Proof of Strength for Engineering Components. So this is, as I had it in my lecture, in the course, always there the FKM guideline. And here So this is regarding to the fractures analysis, and then there is also the Eurofitnab, which there belongs to the SynTab, and the SynTab is like it's a short word for structural integrity analysis. And there you also can find, with this documentation, some documents where shown, okay, how is done a fracture toughness test, what are some main concepts regarding to get some crack analysis and to get some crack assessment. So also for you, because you asked also yesterday, these are the 2 books for the fatigue analysis. So, what I have already drawn here is some typical, or some time sheet, some time series where I was just going through, usually in the lecture. So we have here our x-axis, and on the same time we have here the time series. So here t in seconds or something else. It can be some time information. And of course here we have here the MPAs. So In our analysis, usually, if we go for some candidates, so if we go, for example, for a static analysis, we have here simple cantilever, and on this cantilever we have our cross-section, we have a force, and also here the cross-section. So at the end we do our analysis by m sigma is m over w. So, and this has to be smaller than Fy. So at this point, our force is always, of course, a maximum value to take care of the most impact, the highest impact, and also of some impact which we maybe have not think about. So if we now go for our fatigue analysis, so we have here our cycles. And here our resistance curve. If you always would go with the highest peak, we would sum up end here, and so the amount of cycles we can take are really low. So that's why we have to go a little bit into the loading concepts, and also a little bit into the occurrency and the amount of cycles and the amount of stress range to have at the same time. Of course, also the amount of high peaks, which can be, for example, in this case, something like 100, but also the lowering peaks, which can be here like 1,000, and here like 10,000. So at the end, if you go for your analysis, you're just interested on what is the amount of cycles your structure, your detail can handle, and therefore you have to consider also some other information of your stress time signal to can consider or to get a reasonable amount of cycle, which at the end your detail can take with. So how does it look like? So for example, we have here usually some different structures. So for example, we have here our bridge. Over the bridge there is a nice truck. This goes every day over the bridge, and so due to the crossing of the truck, we get here some information of our on our detail, and therefore we have to get the transfer from our load history, which is something related to the amount of trucks, the amount of cars we have there. We have to get it due to some function transferred from load to stress. So, for example, this is how you would do it if you go for an analysis in the office. At the end, we end up here with our material law, which is here the DSN curve. So, of course, if you, for example, go to analyze something like this, you have different options. You can go there and do some measuring of the traffic, of the loads which are going over your bridge or over your grain structure. Then you have the information about the load history. On the same time, you can go there if you have some further tools to go there, and you can use some strain gauges and you have to put them on the most important points to get a really significant stress time signal, and also by having an idea of the loads which are going over your system and some structural analysis. At the end, you can also get some information due to the strain gauges about to the loads which are crossing your structure. So, and of course, at this part, we also have to a little bit go into the statistics, and therefore, of course, we have some deterministic loads. So deterministic loads are they're possible at any time, and they have a specific value of the load. So, for example, if you say, okay, you have a for example, a truck from the fire safety. You know about the loading of this truck. You know about the weight of the truck at the end. So this truck is usually a little bit heavier than some other specific trucks, and so for this would be for the fire truck, it could be a deterministic load, because at the end you know, okay, at a specific time, for example on Sunday morning or 2 times a week, this fire truck goes over this bridge, and so you have there this loading every day or 2 times a week. Then also if you know about the deterministic loads, the curve of course is reproducible. So what does it mean? Again, we have here our loading, we have here our function, and at the end we have our resistance curve. So in this system everything is defined. So we can define also the loads, the history, and so we can also reproduce it. So, and therefore, okay, if you go now for time signal, of course, this load, the deterministic load, can be harmonic, periodical, or overall time-dependent loads. So, of course, this is something which we had, for example, yesterday. So if something is harmonic, we have here some information about the sinus, and if it's periodical, then it is also like depending on a sinus plus some sinus, so on, and you can estimate the information. If you go for example, to an overall time-dependent load, this would be something like which is continuous. So at the end, some mean value in this case. So, for example, here some death rate, for example. Then at the same time, you have some stochastic loads, and the stochastic loads can be steady or unsteady. So what does it mean? Just if you have a steady load, it is related to a specific point. So you have information about the place, you have information about the process itself. If it's getting unsteady, then it is something which is moving, and you have no further information. Or you have to get the further information, but at first you cannot calculate. So then, how does it look like? So for example, this deterministic harmonic load, of course, here you have a sinus, and at the same time, for example, if you look, for example, to a chimney, you have here the Kalman vortex. So at the end, due to the shape of our chimney, so we have here a circle, due to the stream of our air, we have next to the circle some friction on the chimney, and due to this we have here this shape of the stream beyond the chimney, which is known as the common vertex. So just as you go. So here, for example, the same. So you see here, this would be the round bar, so something which the chimney. And afterwards, you have here the common vertex, so the stream, which is quite irregular. And of course, due to this, you get some reaction of your structure. And this reaction of your structure at the end gives you a cyclic loading. And this cyclic loading at the end results due to, of course, fatigue. So, how does it look for periodical load? So periodical load, for example, can be a human. So for example, you can go over a bridge and to have some further information with, for example, some Fourier expression, or which is also related to this here. You can describe the moving of a person just in a simply engineering model. For the loading, and at the end, of course, you also get some information about the loading due to this harmonic loading, which results or is influenced mainly by the walk of the person over the bridge. So, overall time dependent, okay. We have here some, as I said before, the information, which is just actually occasion, yeah, which is occasion, yeah, that's correct. And so, for example, you have here like an impact on a column, and so at the end, the impact results to a curve which looks like this. And at the end, also with this impact, you get some information or some influence onto your structure. So, if you now go for the stochastic loading, so as you can see here, the stochastic loading also has some time signal, and is during the time it's quite variable. And at the same time, what is here important, the load time curve is not reproducible. So we can collect the information, but at the end, for example, also with the methods I want to go later on, we are not in the situation that at the end we can reproduce this curve again. So, at the end, due to, for example, the unsteady stochastic loads, we have here some different time signals. And of course, all these time signals results or are combined together. And this at the end gives us the information of, for example, this stress peak on our bearing situation at this point. So we have here an influence of our wind signal. Then we have an information of a car going over the bridge. So, and at the end, all this somehow has to be combined. So, some typical failure which appeared there, for example, was in offshore structure. So at the end, there were a lot of cycles due to the wave, of course. And so at the end, this point here failed. And due to the failing, the cross section at the end was the failing part for the offsphere structure, and at the end completely was destroyed. So the unsteady stochastic load, we had already our impact information, and also here we have, for example, some informations due to the system which is working, which you want to analyze, and at the same time you have some information about impact loading. So, for example, this could be in case of Costa Rica, also the information of an earthquake. So this is what is not really, which you cannot really collect, but at the end you have to get an information just due to the impact loading which is on your structure. So now to get the information on what we want to do or what we want to do with our loadings is to collect the information in load collectors, and at the end the methods we have to use are different counting methods. So the counting methods are just giving you the information on the delta sigma, so the value which we want to have, and also at this level also the amount of cycles which are in your time signal. So I just I don't like the order. So what I want to start with is at first a simple one, which is not in the slides. So, but this is the next one I want to go on. So, in the different methods usually we have, we are talking about a one parametric and a two parametric counting method. So one parametric counting method is just giving you the information about the delta sigma. If you go for a two parametric, you also get the information about the R value, and also therefore you have here some information about the mean value of your stresses, and also about how different cycles may be related. So at first I want to go for the one parametric, and the one parametric, for example, is the reservoir counting method, but also it is the span counting method, which is also much more easier, and is at this point, I would say at this situation, to get a little bit into the schematic of the counting method a little bit easier. So, what are we doing? So, for example, if you go for a time signal as this, you can find, for example, I saw in your laboratory, you had some measurement tools from HBM, and in these tools there is, for example, also already applied some or included some cycling counting methods, and so for example, if you apply on a system a strain gauge, you already can go there and say, okay, please use the information from the strain gauge to a counting method, and you already get back there the information. So, and what are they doing is, at first, that they have to get a classification procedure, and this classification procedure is here shown at first. So you have here, for example, the stress range, which is going from sigma max to sigma min. And this interval you have to divide into, usually it's done 18, 64, 128 different classes. So this is just related to the memory. So if you to the memory, and so for example here I used a procedure where I just used 8 to have at the same time good overview. So, but if you go, for example, to a PC, of course, it doesn't really matter. So, what are you doing? You have here the sigma min, you have the sigma max, and this area you divide into 8 equidistant intervals. So, you have here some dx, 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 and at the end you don't know, you have no information at this level about the stresses which are really acting. So you just know about the class of your peak, but you lose the information on the stress amount. So this is something you have to take care on in the evaluation of the histogram at the end. So, for example, now I have done here the classification. So I know that this point has the class 3, this point has the class 2, this point the class 7, 5, 7, 3, 6, 3, 7, 1, 5, and 3, 6, 3, 8, and 2, 5, 3, and here we have the 7. So I said, okay, when a point is on the line, I always take it into the into the higher class. 1, 3, 2, 3, 1, 3. So this is basically our first information we have now on our time stress signal. And now we are just counting the falling spans. So this is the falling spans. So we have here from 2 to 7. Then from 5 to 7, 3, 6, 3, 7, 1, 5, 3, 6, 3, 8, 2, 5, 3, 7, 1, 3, and 2, 3, and 1, 3. So at the end, we get here our information about the classes we have here 1, 3, 3, 2. So this is I would say the simplest way you can do. So you just have the information about the spans. You just take care about the falling spans, and you just sum up at the end the same, where you have, for example, here the 5 and here the 2. So always the deltas of the case, and at the end you can draw your histogram, and you know about, if you have here the difference of one class, then you have, for example, a delta sigma which is related to the dx. So dx times k. So this is, as I said already, the poorest and the easiest one. So the next one, for example, would be if you say, okay, this is not really a delta sigma as how it related, for example, to a sinus. Then you can go there and say, okay, I just take the falling spans where I also get the information on a rising span. So for example, you can combine this point, this span to this span, but at the same time, of course, you lose a lot of information on the damage which is acting actually on the structure, and so the amount of cycles is really poorly assessed. So the next one is the reservoir method, and the reservoir method is what you can see here. So the reservoir method is also a one-parametric counting method which detects the stress ranges, but as I already said, it is not detecting the mean value, so it doesn't give you an information about this the stress ratio. So what is the idea behind is quite easy. So you see like the time signal as information of hills and valleys, and at the end you completely fill everything with water. So due to this, you know, you have here, like at the first load cycle, everything is filled up with water, and at the same level, you're going to use here the information just from the classification procedure. So you know you have here the 1, and the 1, and it doesn't matter if the 1, for example, is here or is here. So in the next stage, you take the lowest peak. So for example, this was in our case here the 1. In this case, it is the 8. And you just say, okay, at this point, I make a cut, and all the water inside your system is running out. So due to this, at first you have here like a water stand which is going from 1 to 8. From 1 to 8, and all the water is running out. So at the end, you have here, at this part, a level which is here, and you have a level which is here, and you have a level which is here. So just by cutting out here the 8. The water is running out, and now you have some new full values, and you say, okay, I go a step further. Inside this value, I have here the 7. I cut up the 7. The water is running out, so I have here 2, 7. And at the end, cut up this, and I get the information of 3, 5. And this valley is completely dry. I go to the next one, cut up here, cut up here. So I have here the information from 3, 6 and 3, 5. So this valley here is completely dry. So now I can go cut up this. I have 1, 3 and 2, 3. Also here, completely dry. So at last, the last valley, which is still full of water, is here this valley, which is going from 2 to 7. So now also I have to choose which one do I take. For example, I go here, I cut up this one, so I get the information from 2 to 7, and here from 3 to 6. So the last value I have is here from 3 to 7 and from 5 to 7. So, and at the same time, I have done estimation where I said, okay, here it is filled up with water. I just think about the energy which is inside the, or which is acting on the system itself. And again, I just can go there and now also get the information. I have here, for example, a span from 7. I have here a span from 5, 2, 3, 2, 2, sorry, 2, 1, 5, 3, 4, 2. So now go back. So I have here now a span of 1. For the 8, still 0. For the 6, also 0. For the 5, I have 1, 2. And for the 4, I have here just 1. For the 3, I have 1, 2. And for the 2, 1, 2, 3, 4. And for the 1, also just 1. So if I now compare both, at the end I had here numbers of cycles which are 1 plus 3 plus 3 plus 2 plus 2 is 11. And the same side, 1 plus 4 plus 2 plus 1 plus 2 plus 1. So at the end, it's still 11. That's correct. 1, 2, 3. Yep, still 11. So why? So if you go, for example, and do the same for a longer time series, then at the same level, yeah, you would not reach the same amount. So it would really be different at the same time. So, and also, at the end, what you're getting is at the ending is here the multi-stage load spectrum. So this is what I called also the stress collective. And with this stress collective, at the end, we have some information about the loads which are in the system and also about the damage which is somehow acting on the system. So, and now you have seen this two kind of different approaches, which are just really schematic, following an idea how it maybe can be possible to sum up somehow the informations, and at the same time, this is not really related to the material behavior itself. So that's why we have to go a little bit again into the cyclic material behavior. And the cyclic material behavior, or the material behavior itself, is for steel described by the massing law and the massing memory behavior of materials. So the massing memory behavior of the materials is somehow also related or mainly described here with the definition of the cyclic stress strain law, which is here done just by the Rambert-Oskrodt definition. And so as you can see here, you start at this point, follow your stress strain curve. You have at this point a turning point, so you have to assume a new coordinate system. At the same time, you go down. You have at the first time it is following the elastic part. So this is what you can see here. And after getting some elastic part, you go up, you have a new coordinate system, and again, you meet here at the same curve, which is just done by static cyclic loading behavior. So for example, if you would have some softening behavior or some strengthening behavior of the material, then of course you would not reach the point again, but here we just talk about the behavior when it is already gotten stabilization. So due to this, we have the three mainly points of the massing memory behavior, and so this means the M1 after closing of the hysteresis, which started on the cyclic stress strain curve, the stress strain path again follows the cyclic stress strain curve. So what does it mean? As already explained, we are going up here. And at this point, we say, okay, we reach our first peak, we go down, we close the hysteresis, and again, we follow our stress strain curve. So the M2 is after closing a hysteresis, which started on the hysteresis branch, the stress strain path follows the curve of the original stress strain hysteresis branch. So what does it mean again? So for example, we have done here our first loop, and now we are still on the stress strain behavior. Again, we reach the peak, we go down, and the huge hysteresis is still not closed. So this is still open hysteresis, which can take some amount of energy or some damage deformation. And at this point, we get a new hysteresis. This hysteresis is open, it's closed, and again, we follow the old big hysteresis. And at the end, this hysteresis, of course, is closed at this point here. So that's why we can go for the last assumption. A hysteresis branch which started at the cyclic stress strain curve ends as soon as the amount of the stress strain reaches its starting point in the opposite quadrant. Again, the stress strain path follows then again the cyclic stress strain curve. So what is it again? We have here our coordinate system for the huge one. So we go here, we go to the opposite quadrant, and again, go to the starting point. So at the end, this hysteresis is closed at this point. So, and due to this, there was the idea to create also a counting method which is related to this material behavior. And this is mainly known as the rainflow counting method. And so what you can also see here, so for example, you have here the time signal, just to get the idea, turned around by 90 degrees. And then you see here the water is running like in a, I don't know, usually for kids you have some small some games where you just put the ball on side, and then also the ball is running through this tool. And so also here the same with the water. So you start here and just going downwards, and at the end you can somehow go there and calculate the rain flow or the closed hysteresis. And so how does it look like? So for example, at this point, if we start here, at the point of the if you start at this point here, so on the highest peak, the water is going into this direction. At this point here, it is falling down, and at the end is closing here this hysteresis. So therefore, of course, we have to skip this point, because otherwise we would also have here a water falling, but we said, okay, the water starts here, and there at this point, at the starting point, there is no water running beyond this point. So then on this side, okay, we have the first closed hysteresis. So this is the big one, hysteresis. So we have a hysteresis which is going from this point to this point to this point. So the next one is going from this point to this point. And here again, the water is falling down. So here again, we have a closed hysteresis. And this point here, so this level, we have also water falling down to the line here. But as you see here, this hysteresis is closing from here to here to here. And mainly this hysteresis here would start inside the other hysteresis, and this is not possible due to the massing memory behavior, so which we have here. So we always have here a hysteresis which is starting and closing, but there is no hysteresis which is starting here, going here, and then closing here at this point. And that's why we have to skip, or we cannot close the hysteresis from this point to this point and to this point. And so this is mainly just a water drop which is falling down here. But for the system, for the accumulation or the counting of the closed hysteresis, we get no information there. So at the end, we have to do this information. Here, the information from a signal which goes from here to here to here. So this is the stress range. But also due to the information about the classes, we also get the information about the mean value, which is of course here related to the mean value, which is from this class to this class. And also we get the information about a falling hysteresis or a rising hysteresis. So this would be for example, as you can see here, you have a hysteresis which starts at the peak and is going downwards, and then again is going upwards. and this would be a falling hysteresis. And at this level, we have a rising hysteresis, which is going from this point, so from the lowest peak to the highest peak, and again to the lowest peak. So let's go to the system here. So we start now, okay, just think and turn 90 degrees to have maybe a little bit easier information. And I have to, sorry to delete this. So, as I said before, at this point, we have no water drop falling down, so we have no water which is going into this direction, so we just can skip this point, and our water starts to go in from 3 to 2. So, at the point 2, our water is going into this direction and ends up here. So at the end, we have here a closed hysteresis, which is going from 2 to 7 to 2. And inside, of course, we have here also some information. So at this point, also our water is going from 7 to 5 to 7. And here, again, from 3 to 6 to 3. So, at this level, if we would go, for example, at this point, okay, we could assume that there is also some water going down, but as I told already here, we have here the closed hysteresis. This hysteresis starts inside the small hysteresis, and so we cannot account about this one. The same is here. This one we also cannot go with. So, the next one we have here is starting at this point. So at point 1, the water is falling down to 1 again, and we get here the hysteresis from 1, 8 to 1. And also, again, have here the information from 5, 3, 5, and at this point from 6, 3, 6. The maybe possible hysteresis from 3, 6, 3 again is not valid. Also from 3, 8, 3. So, and now we have again our point at 2. So here the water again is falling down. We have the closed hysteresis from 2 to 7 to 2. And at the same point from 5, 3 to 5. This one we have to skip. And last, we have here our information from 1, 3, 1, and the information from 3 to 3. So this is basically how is going in the rain flow analysis. And at the end, we have a matrix, which is called the rain flow matrix. Which is just looking like this. So we have a matrix due to our classification procedure from 1 to 8. So also here from 1 to 8. We know that we have no circles which are going from 1 to 1, from 2 to 2, 3, 3. So this is something where we have no information due to the cycles, so we just can skip it. Then we have here information from 2 to 7 to 2. We have this information 2 times, so we can go there. So this is starting side, this is ending. And so we know we have here information which goes from 2 to 7 to 2, and this 2 times. Then we know about the 757. We have here just once. Then we have here the 363. Just once. Then our information from 818. Just once. And from 535. 2 times. And the information from 636. So before we had 366 and now 636 once. And also 131 just once. And the 323 just once. So this is what is at the end our rainflow matrix, and also the information on the information of the load cycles, of the stress ranges, and also due to the mean value, the R value. So what do we know now? So that, for example, we have here, if you go from 2 to from 2 to 3 to 2. 2. Then we know that we have here, for example, on this side, a hysteresis which is going like this, and on this side, a hysteresis which is going like this, and just divided by the mean diagonal of our matrix. So the next information is what we can also get here is the same is our log collective. So we can go again, we see here we have a whole amount of cycles which are 2 plus 1 plus 1 plus 1 plus 1 plus 1 plus 2. So at the end here we just have 9 cycles. But these 9 cycles are related to the information of the material behavior, so of the cyclic behavior of the hysteresis. And also at the same time, we now can start and go and define our load histogram, but also give some information if it's really wanted about the R value. And as we have seen, the R value gives us the information on the stress ratio, so here about the resistance curve and also about the damage onto our structure. So now just to I just want to give here instead of the classes some information on the stress range, so that we can go again into your damage calculations and end this example with the accumulation of the stress ranges again. So for example, if we now say, okay, our dk is 20, then we would have here for the first stress range here 20 MPa, here the 40 MPa, 60, 80, 100, 120, 140, 160 MPa. And this is so the information from one time signal, time stress signal we have. And for example, we now can say, okay, this time stress signal, we have this during our measurement of 1 month, of 3 months, 100 times. So due to the information of this time stress signal is inside the amount of, during the time of 3 months, 100 times. So we know, okay, we have here at the end 200, 200, 300, 300, 100 cycles for 3 months. So again, we can go there, and we know now, okay, we have for 100 MPa, we have (200 cycles with 100 MPa. We have, and then R value of 0.5. Then we have here the 80 MPa again. Sorry. Then we have 60 MPa with 300. We have here the 40 again with 300. And the last one is 20 MPa and with 100. So at the end, our collective is looking like this. So usually we would assume if you go for real long-term calculations, we would have here at this level more cycles on the lower part and less at the higher part. And of course, we have to choose again here, for example, for our detail. So to have due to the low amount, we just go here for a detail, which is, for example, here a really thick part. So we have huge dimensions, huge blades. So we say here we have our 50 MPa. And so at the end, we end up here with a damage accumulation, a linear damage accumulation for 3 months of at the end from 0.02 regarding to the low collective we had before. So yeah, so this is basically what is related at this point to the load counting methods, and which was also at this stage, yeah, the finishing example on what you can do regarding to the fatigue assessment and regarding to the loads which you apply, and at the end how you can end up by the by the assessment, and hopefully at the proof which fits into the concept of your design and which also fits into the design of the inspection intervals or something else. So the last minutes I would use just for some questions. If there are some questions, please ask them, and so to have some feedback on the topics itself, and also to have some feedback on topics maybe you're also interested a little bit more, to have some idea how to continue and how to work with these tools. So. Okay, so thanks for joining the last 4 days, and yeah, hopefully you have some ideas how to go forward with these tools, and then have a good day. I'm finished, so.